Quarks are like the coolest thing ever. Really manipulated directly. You can't hold a quark. You can't measure a quark on its own. There's lots of types. I think like 12 types of them, but you can't ever hold one. You can't manipulate one directly. You can't break it down into. You might be able to break it down further, but I don't know. That's the edge of my knowledge. But anyways, they're not things. So why does it even make sense to talk about them if you can't do anything with them? Well, because so like the early 1900s, we figured out that the universe is not continuous. Like you can't just zoom in and eventually, it always has this curved outline. You can't zoom in like you can on a vector image on a computer where you can always get closer and closer and closer and closer and closer. Eventually, you'll find that it's not a smooth circle. It's little individual atoms that are building blocks, and atoms are the smallest indivisible part of matter. If you define matter as things that interact with the big four forces, strong nuclear, strong, weak, electromagnetic, and gravity, right? So atoms are the smallest things that interact on all those levels. Atoms supposed to be indivisible, but then we later figured out that, oh no, there's neutrons, protons, and electrons. Of course, we figured out protons and electrons before neutrons because neutrons they're neutral, so it's harder to manipulate them. So atoms were, mind-blowing that things aren't smooth, right? You go down and you can zoom in far enough that you'll get the smallest piece of something that has the same properties as the whole. Like a hunk of gold is made up of trillions of individual parts of gold. And if you split that part of gold smaller, it no longer has the properties of gold as far as conductivity, temperature, reactions, all that. So if you split an atom of gold, now you have something that's no longer gold. So it's the smallest chunk of something that makes sense as part of the whole. If you split it farther, you're not changing it into something completely different. Quarks are similar in that those parts of atoms that you can split it into, protons, neutrons, electrons, those can be split even further. Well, they can't be split further, but what you can find out is that if you collide them in these insanely high energy events, you can recombine them, and suddenly from this particle you get a bunch of gamma rays. You can combine these two protons, and you sometimes end up with showers of things, and sometimes you don't even know. You don't measure those things directly. Instead, you measure the radiation that happens after. Okay, you combine these two things and you get this cool product, but it only lasts a fraction of a second, and it breaks down into these other products, and those are the things that really last longer than a few seconds. But the intermediate thing you can kind of tell because you get these showers of radiation coming off. So those products that happen are not the quarks. The quarks describe what you can possibly get out. So they're the ingredients of these fundamental particles you're smacking together, and you find out if you take this one type of thing and you combine it with this other type of thing, you can't just get the whole rainbow of types of particles coming out of that. If you take specific types of things, you can only get a handful of specific types of outcomes. And let's say you'll never get something that has a charge coming out of it, or you'll never get something that experiences the the electromagnetic force or something like that out of it. So quarks are just kind of a thought of this fundamental thing. They can only combine in certain ratios, which is really weird because there's not even a whole number of things. It's like one is minus a third, one is plus 2/3, there's a minus 2/3, and so you can only combine like two of these with one of these, or three of these with two of these. And again, you can't hold the individual quarks, but when you smash things together, depending on what you started with, that will limit what you can get out of the smashing. So quarks are fundamental things that can you can deduce what they are based on how the different combinations behave. Like, oh, smash a neutron with a proton. Here are the variety of things I can get out of it. That must mean the proton and the neutron have these types of quarks. And you find out that particles can only exist if they have a whole number combination, and that whole number combination can be like a zero. So if you have a negative 1/3 and a positive 1/3 combined, that would theoretically make a stable particle. You could do 3 1/3 or a bunch of 2/3 together, things like that. Although it's not like just anything goes. I think there's some further rules, and that's why you get into different types of quarks where they have different names. Like, oh, this is charm, this is strange, this is up quark, down quark, that sort of thing. So there are slightly different rules about each one, but I think it's really cool that they have this whole number property where you can kind of predict future ones by saying, what if I combine these ones? We haven't detected it yet, but maybe if we build a larger particle collider, you can detect it. Cool stuff. You can make predictions and say, that's why they're not just smashing things willy nilly in the LHC and other big colliders. They're saying, I know in this region of energy, I should be able to see this particle if it exists. So quarks are really cool for that. They help predict things, even though you can't measure them directly. I think that's really neat. What was your question? Microgravity? I need to move. Darn, I can't move this. My video preview is in the way. I think your other thing was like microgravity pockets. I'm 50% sure you made that up. And then I Googled, and now I'm 95% sure you made that up. But if it's real, then interesting, and I want to learn about it. I know that wasn't 20 minutes, but